Hello, class. Welcome to Module 4. This week we're discussing instrumental variables. First off, congratulations on being halfway done with the course. Hopefully everybody's having a good time thus far. So this week we're going to be talking about instrumental variables. And in order to jump into that, let's recap omitted variable bias. I'm going to jump to, well, excuse me, there's three documents or three resources to look through this week. The lecture itself, which we're going to go through here in the video, the PowerPoint presentation, which we're going to go through a little bit as well, bias correction through instrumental variables, and there is an example document of how to go through and complete this. This will be helpful for the lab, but I'm not going to go through that with you here. That's going to be for you to go through. Okay, so starting off with the lecture, again, I wanted to touch base again on what omitted variable bias is. So let's say that we want to look at, and I'll just use what's going to be in the lecture. Let's say that we want to look at the effect of education, that'll be our policy variable, on Y, that'll be our outcome variable. We're going to call it wages. So we want to know the effect of education on wages. If we were to, or we have an inherent problem because in a lot of real world situations, there's variables that we can't control for or um, might not include. So that could be intentional, where we left out a variable that could introduce bias. It also could be simply that we can't measure the thing. So the example we're going to see in the lecture is our omitted variable will be ability. That's not something that we can measure, but it is something that affects education and it's something that affects wages. So how do we control for this? How do we try and get the most accurate effect possible? So just to give you an example, let's say we were to do sorry, I'm scrolling through, don't get lost on all of this. I don't believe it actually has a naive model. Might not list the naive model in here. Okay, forgive me, let's come back up here. So when we're running our model, so again, ability would not be included in it. So let's actually just type this out. Let's say we want to run our model with just education on wages. We'll do it R style. That'll look like wages. And oops. Oh, that's odd. Huh. My keyboard in this PDF editor will not let me put in my little squiggly guy. Okay, we're just going to put equals for now. And we'll just put it as education. Let's say that this is the model we want to run. We can't include ability because we can't measure ability. So what would happen is if we ran this model with just education on wages, not accounting for or controlling for ability, what would actually happen, and this should come back to you, is it's going to give us an improper estimate, where in this instance, everything I'm drawing in red right here, this is going to be the variance that's accounted for or attributed to education. So this is going to be the explanatory power of education on wages. Now the problem is though, is because we have this unaccounted for and frankly unseen variable ability, it gives us an improper estimate. So really, if we wanted to do a full model, let's say we could measure and account for ability, if we were to run the model and include ability as a control, then the outcome, the explanatory power, would be represented by just this area. This is the explanatory power of education on wages. Excuse me, ignore that last tiny bit. Uh, it would just be this the only excuse me the area where x1, our policy variable education, overlaps with y, our outcome variable wages, not where it overlaps with the omitted variable ability. Okay, so this is ultimately what we're talking about here. How do we get the most accurate estimate possible when we can't account for something, a variable? So we use something called an instrumental variable, and ultimately what that looks like is we include a variable that is correlated strongly with our policy variable, and it is correlated with our outcome variable. Again, y is going to be wages, policy variable x1 is education in this example. Omitted variable is going to be ability, and z, this is our instrumental variable. You see how it's strongly correlated. There's a lot of overlap here between z and x1, and there's some overlap between z and y. However, it's only through z that we get to y. So think of it as like a lever. The only way that we can get our instrumental variable to explain or to relate to our outcome variable is somehow it's almost like a lever that pushes on our policy variable, and then it overlaps with y. So that might be confusing. Don't let me lose you there. We'll come back to it. But ultimately, an instrumental variable would visually look like this: something that's strongly correlated with x1, our policy variable, and as a byproduct of that, it's related to our outcome variable. But it is not correlated with our omitted variable. And to give you the overview, basically what we do is we use the instrumental variable, so this overlap here, to essentially replace what truthfully would be the explanatory power of our omitted variable. So because we can't account for the omitted variable, we insert an instrumental variable, which essentially does the same thing, but there's some very important qualifiers in order to do that. So I hope that makes sense. We will come back to this a little more, but I'm going to go into the lecture now. Um, this week there is an option to use the AER package. I don't recall the lab itself requiring you to use that. Let me just check real quick. No, okay, so the lab doesn't require it. It is something that you can use, that package, but the lab doesn't require it. And it's not actually used in our lecture, but it's one that you can get familiar with, and it is helpful for working with instrumental variables. Okay, so in Stargazer, we'll be using once again. You should all be used to that by now. So under what circumstance do you need to use an instrumental variable? We've already kind of talked about that. If you know that there's some kind of a omitted variable and you want to make sure that you get a more refined or more accurate measurement of your policy variable, help eat up some of that explanatory power that shouldn't be there, some of the characteristics, and then the mechanisms behind it. So what we're going to basically do is we're going to learn what it's for, how to use it. The how to use it part's going to take, there's two stages that we're going to go through. I'm getting ahead of myself. We'll cross that bridge when we get there. So it's there to address omitted variable bias. And I apologize. It's late tonight. I've slipped a few times and said virus or virus instead of bias. So if you hear me have a slip of the tongue there and say the wrong word, don't give me too much grief for it. Okay. All right, so we talked already about what omitted variable bias is. It cannot be observed or measured. It's problematic, especially if it's significantly correlated with both the outcome variable and the policy variable, as we've already discussed. X2 here representing our omitted variable. The dashed lines because we cannot see it. We can see that it is correlated with our outcome variable and our target, or sorry, policy variable. So we can see the overlap here. So realistically, we want the truth of the relationship in the effect of X1 on Y without the accounting for the omitted variable. A and B would be our coefficient, which is not true though, because it's adding extra explanatory power to the target variable, which is, sorry, to the policy variable, when in reality it shouldn't be there. So we that would give us an overestimated effect. In some cases, an underestimated effect. We'll actually see that at the very end of this lecture. But for now, just think of it as giving us an overestimated effect. So I hope that that makes sense. So ultimately, it's just accounting for that bias. So a full model, if we were to be able to control for that, sticking with our education, wages, uh, and ability, a full model might look something like controlling for, let's say, wages, and we have our policy variable, which is education. Oops, I didn't spell it right. And let's say that our control here would be ability. So if we could measure ability, then we could have our traditional model set up, and that would be able to give us a correct result. However, because we can't control for ability, that ultimately leaves us with a naive model where this variable is excluded, and once again, it's going to overestimate the effects. Like I mentioned before, if we leave it out, which we can't put it in because we can't measure ability, it would over assume the effect of x1 on y, leaving us with the overlap here of a. However, in reality, this omitted variable would actually take up some of that explanatory power where A should be here and it should only take up that much space, whereas it takes up this. So it overestimates our explanatory value power, explanatory power. My goodness, please offer some grace as I am going through this. So know that when we have a variable that's omitted and it is correlated with the policy variable and the outcome variable, as we see here, it's going to affect both our slope and our standard errors of the model. And again, we've already gone through that. So the instrumental variable, bottom line, is going to help us reduce the omitted variable bias because it's going to help us explain or take away, think of it as a way of refining the measurement of our policy variable's effect. It's a way for us to help hone the true effect of our policy variable by removing this, okay? It's really the best way to think about it. So it gives us a more precise effect. We're substituting our omitted variable, which we cannot measure, and include with an instrumental variable, which essentially will not the same, but it helps us to approach that. So very important though, the instrumental variable is not correlated with the omitted variable. So you'll see here, the circle of x2 has no overlap with that of z. So in order to have an instrumental variable that works, it cannot correlate with the pardon me, the omitted variable. So an example we'll be going through is the education wages, omitted variable being ability, and then the instrumental variable that we'll be discussing is father's education. So how much education your father has would influence the amount of education you have. Again, our treatment variable. And that would also influence through that our wages outcome variable, but it wouldn't necessarily be associated with our ability. And we'll talk more about that. Again, forgive me, I'm kind of getting ahead of myself here. So a way to look at that visually too is we have our omitted variable, ability, which is related to our outcome variable, wages, and it's related to our policy variable, which is education. So more education, we assume higher wages. We know ability would increase your education, and it could influence your ability, or sorry, your wages part of me. And then again, we'll talk about father's education, which is what is used in the one of the following examples for our instrumental variable. We wouldn't expect that father's education would somehow increase your wages. So the way that an important concept is that the instrumental variable is going to be related to the outcome variable. Again, father's education, wages, you wouldn't think that wages is going to be, you won't get paid more because your father has more education. So it's not directly related. However, it is related to wages through education because we would argue through theory that the more education your father has, the more likely you will have more education, which would then influence your wages. So again, getting ahead of myself here, but that's ultimately what we're going to be talking about for the most part today. So we use the instrumental variable to partition, to separate, in order to distinguish the differences, the variance of the policy variable into two parts. So one part, which is going to be part A, that's going to be the part that's highly correlated with the instrumental variable. So we have, again, our policy variable here, x1, instrumental variable z, and our omitted variable here, x2. What we're going to do, what it's saying by part one, and what we're going to do for the two-step, is we want to identify this area of the instrumental variable and treatment variable overlap, the the variance there. So part one is to distinguish what that value is. And then what we'll do for part two is use that value, those predicted values, in a follow-up regression in order to do part two, which ultimately we replace the fitted variables there that we get from part two into our final model. Sorry, I'm getting ahead of myself, folks. It's one of those nights. So ultimately, we first want to figure out what this correlated area is, and then we want to also use that to figure out what this area is, B and C. So this would be the unexplained portion. So bottom line, we want to identify A so that we can make sure that we're leaving B and C out of our final model. So looking at it again, let's continue with our um, R. So if we're working with the example of education on, sorry, wages. So if this is our original model, and again, I don't know why it doesn't let me do the squiggly, so we'll just do an equal sign, even though that's not syntax correct for R. We'll say wages on education and ability as a control. So that would be our full model if we could do that, but we can't do that because we do not have the ability to, well, measure ability. So that would be the ideal model if we could. Because we can't measure ability, we have a naive model, which is the ln function wages, no squiggly line, education. Okay, so that's a naive model. That's going to give us an overestimation of education because we're not able to control for ability. So because we can't do the full model, we move into the instrumental variable. First step being we switch this around. So you'll see it listed out here, but again, I'll put it in R form. So we have stage one for instrumental variable. What we're doing here is we simply run a regression first where we're swapping the policy variable with our instrumental variable, and then our policy variable becomes our outcome variable. So we would change education to be our outcome variable, and our instrumental variable, which I mentioned before, and it's in the next example, so I'm just getting ahead of myself here, father's education. So that would be our instrumental variable. So essentially, we're just going to first regress our instrumental variable on our original policy variable. From that, we're going to be able to have our predicted values that we can then include in our next model. Okay. So first, we're going to regress father's education on education. That's going to give us the overlap here, the covariance of the instrumental variable and our policy variable. So let me finish what I'm doing, working with this. So we're going to do education becomes our outcome variable, and father's education becomes our policy variable. This is only for stage one for the instrumental variable process. And then second, we would do stage two, which once again will use the predicted values from this stage one model, and we would use that in place of our treatment variable. So that would look something like wages, go back to our original, can't do a squiggly line, use the equal sign instead. So x1 hat, if you don't recall, x1 hat, oh boy, it's way past. We'll get to it, but x1 hat is just the statistical terminology used to explain the predicted values. So it's going to be when you have that little hat over x or the little hat over y, that's going to be the predicted values. And then you have the bar. So don't get it confused with x bar, y bar. Those represent means. This represents the predicted values based on our model. Okay. Then we would just run this, and that would give us our most accurate effect. So to recap, stage one, we determine the overlap here between our treatment variable and our instrumental variable. Stage two, we use the predicted or the fitted values from this regression here, stage one, and then we use those fitted values as our treatment variable. So we will replace education. I should probably type that out here. Education, this would be wages now because that's what we actually want to measure. And then our treatment variable becomes the fitted values from stage one. Okay, hopefully that makes a little bit of sense. We'll go into it within more detail. So I've been prefacing or foreshadowing, whatever you want to call it, the next several minutes, well, probably almost the rest of our entire time, we'll be talking about this example. So hourly wage, education. We want to know the effect of education on hourly wage. We want to know that relationship. So ultimately, how much does your salary increase for any additional year of education? That's the basic question. Here's what our model would look like. Again, this is the naive model. Here's some of the information we'll be working with. We have wages, our outcome variable, education, that's going to be our treatment variable, ability is our limited variable, and experience is going to be our control. And then in this example, father's education is going to be our instrumental variable. Okay, so we have the individual's hourly wage in a given year. Policy variable is the number of years that individuals have spent in school. Look at some summary statistics here. So again, based on research, scholars have encountered that ability bias affects the relationship between wages and education. So once again, ability, our omitted variable here, is related to both education and wage, and you can see the relationship overlap here. So circles back to what we had already discussed. So basically, higher ability both influences how far you go in education, how much education you get, as well as wages that you may receive. So ability is something that we cannot measure, but we do need to control for. And by excluding it, it creates that bias. So once again, full model, this is what we already looked at here. If we could include the omitted variable, this would be perfect. That would be a strong model. However, because we can't, we're left with a naive model, excuse me, a naive model, which in this instance would ultimately overestimate our effect of education on earnings because it's basically using some of the omitted variables impact on earnings and just absorbing that into education because once again, it's not in our model. So let's look at these. So we have our LM function for our full model. We have wage, education, ability, experience. That's the full model. That would be a more the most accurate slope. Then we have our naive model, which leaves out ability because once again, we cannot measure it. So let's compare. So in our full model, this is our impact here. However, in a naive model, we can see that it overestimates because it's taking some of the explanatory power that would have come from ability and it's simply adding that to education because our model doesn't have it listed. So it has to go somewhere and education sort of eats it up, Pac-Man style. It eats up that extra explanatory value because of the overlap. Okay, hopefully that makes sense. All right, so some critical components of an instrumental variable. So number one, it has to be correlated with the policy variable. Come back over here. So as we mentioned before, it has to be related with the policy variable. We see that it has a strong relationship between the instrumental variable and the policy variable. It has to be, sorry, it is correlated to the dependent variable, but only through the policy variable. So something we'll look at shortly is um, some relationships plotted out between the instrumental variable and the outcome variable. So if we were to just look at, if we were to just plot it out, we would see that there is a relationship between the instrumental variable. In our case, we're doing father's education with our outcome wages. But this is where we have to be able to argue that it's only through the effective education. So, and we'll be able to test that later. But ultimately, this is what we mean by through. There's no overlap sorry, no overlap between z and y outside of x1, our treatment variable. Okay, and then it cannot be correlated with the omitted variable. And we can see here that there is no overlap between our omitted variable and the instrumental variable. Okay, so those are three criteria in order to have a solid instrumental variable. So now number one and number two, those can be tested. So we can test the relationship between the policy variable and the instrumental variable. We can test the relationship between the dependent variable and the policy variable. And there's ways that we can test to make sure that it's only through the policy variable, which once again we'll show you. And then last one, it cannot be correlated with the omitted variable, and that's one that it can't be tested because once again we can't measure ability, so we can't test the relationship between our instrumental variable and ability. So it has to be backed up by theory. So that means some research that's out there. You have to create a theoretical framework to argue that. Okay, so sticking with the examples we've been on, I mentioned already we're going to use an instrumental variable, father's education. That's the one we're going to pick, and it's based off some data. So individuals who come from more educated families are more likely to stay in school longer, and especially when fathers are more educated. But one's father's education has little or no direct effect on hourly wage. Okay, so that's once again uh, what we're explaining when we say through. You're not going to get paid more because your father has more education, but through the influence of your father having more education, you may get more education and therefore make more wages. Okay, that's what we mean by through. So we can test these by looking at some correlations across the variables in our data set. So let's look at the first graph. We can see here education, father's education on education, strong positive correlation. Father's education on hourly wage, there is a positive relationship, and that's to be expected. We'll see later how we can test to see that it is not directly father's education and wages, but it is father's education through education, then affecting wages. And we can see that the correlation here, there's if we could measure ability, if we could measure ability, so this is just an example, we can't. That's why it has to be backed up by theory. Father's education and ability have no relationship. Okay, so we've got the steps. Again, it's two stages. First, we want to estimate our policy variable based on the instrumental variable. That's what I meant before by we swap. So we replace our outcome variable, which originally was wage. We replace it with education, which was our original policy variable, and we insert our instrumental variable to be our treatment variable. Okay, so I'm gonna say it one more time. Don't get annoyed. Our main question, our main research question was our dependent variable was going to be wages. Our independent variable was going to be education. Oops, probably should put that. And here we just have experience being a control, which you would include your controls in stage one. So don't leave those out. Okay, so this was our original question. So stage one for our instrumental variable, you would move the independent variable or our treatment variable to be the dependent or outcome variable, and you'll insert your instrumental variable to be your treatment variable or your policy variable. Sorry, there's a lot of synonymous terms that can be interchangeable, so don't get caught up on those. Okay, and then we would run it just like we would run any model. So we do save this first stage, and then we have the model itself, print it out, and we can see our output here. And we're going to get to this later, but we have to test the F statistic when we do this, so we'll circle back to that. So now we want to take that and we want to estimate our dependent variable, and we only want to use, though, our predicted values from that first model. So now we can see this is our original model we wanted to ask. So what we're doing now is instead of using education in and of itself, we want to use, we're just going to call it x1 hat here, which is going to be our fitted values from the first stage. Okay. So this says education, but it's technically not going to be education. It's going to be the fitted values or predicted values from the first model. All right, so second stage, we can see this here. We're going to save it. So fitted function, first stage, that was the name of our first model where we had the treatment variable as the instrumental variable. The dependent variable was education. Save that to the x1 hat. And then we're going to run the second stage. So it's the same thing. We're going to just run our normal regression. Instead of education, though, we use x1 hat. Those are our predicted values. And now we can see the different models laid out. So if we can measure ability, that's what we have here for the full model. We would get this coefficient for our education. And forgive me, I can't remember the context. I don't remember exactly what these represent. We have the naive model, which is just leaving ability out altogether, introducing bias. And then we have our instrumental variable, where we can see we regain the true slope, 8.76, 8.76. So in the perfect world, we could measure ability, but because we can't, an instrumental variable brings us back to a far more true slope, where we can really see the actual effect of education on wages. Okay, hopefully that makes sense. It's pretty straightforward. Don't get too caught up in any of it. And we'll continue going through it, but it's really that simple. It's if we expect an omitted variable, we can use an instrumental variable to correct for that. Okay, and just as I already said, it the instrumental variable model going through those stages using the fitted variables as our treatment variable, it allowed us to recover the true slope. So let's look at this some more. Let's go ahead and plot out some results. So we have ability, if we can measure it, and education. And one thing too, in case anybody gets caught up on it, residual error, those are technically different, but usually used interchangeably. So just know if I'm referring to residuals or if we're talking about the same thing. I'm talking about residuals. So we know that the omitted variable bias, it results from the correlation of our policy variable and the omitted variable. So once again, visually, that's this right here. So we know that there's overlap or relationship between both outcome variable and treatment variable. And we can see that here. If we could measure ability, we can see the relationship between ability and education. Our omitted variable is correlated with our treatment variable. However, very important, once again, the instrumental variable, it is correlated with the policy or treatment variable, but it's not with the omitted variable. So because of that circumstance, we can use the instrumental variable, and that allows us to separate that variance into those two sections we already discussed. So once again, a couple things I want to remind you of. We already talked about it, but once again, x hat, y hat, the hat itself, that's just explaining predicted values. The don't get it confused with x bar, y bar, which is the mean values. Okay. So when we talk about the x hat, we're talking about the x1 hat, excuse me. We're just referring to statistical jargon for predicted values. So the x1 hat, this is going to capture the portion of education that's explained by father's education, overlap here. And then the residual, is just the actual value minus the predicted value. Pardon me, that's the part that's not explained by um, pardon me, the part that's not explained by father's education. I apologize. This should say the instrumental variable. Oops, goodness gracious. Okay, moving on. So let's earlier I talked to you about how we can plot or there's a relationship between the instrumental variable and the um, outcome variable only through the policy variable. So once again, there's a relationship between father's education and wages, but only through education. And by plotting the x hat and the residuals, it allows us to ultimately get to see that. So we want to plot those two different graphs. We can see here our models. You can get the predicted values just by using the fitted function and then saving that to the x1 hat. And then same for residuals, residuals, name your model, and save that to an object. Now I want to point this out because we've used predict in the past. I don't think we've used fitted, but fitted, that just allows you to get the predicted values from the values that exist within your data set. Predict allows us to use find data points that are outside of our data set, but fitted just takes the actual data that was included in our model or within our data set we're using in our model, and it gives us the predicted values from just those. Okay, so we have here ability, if we could measure it, our emitted variable, and its relationship to the instrumental variable, um, sorry, the portion of education explained by the instrumental variable, and we see that there's no relationship. So that's just telling us, like in this visual, there's no relationship between father's education and ability. If there was an overlap, then this would be correlated and show that relationship. And over here, we can see ability, if we can measure it, and then the residuals, or the error from the model. And we can see that there is a relationship because that's the component that is correlated between education and ability. Okay, so that's all that that's showing us there. So something interesting, and this is just a way to demonstrate how if we just took education or a treatment variable and we looked at that, plotted that against wage, our outcome variable, it would appear that it's more highly correlated than if we just plot the predicted values against wage. And that's ultimately just because we want to get the most accurate reading, or the most accurate estimate of our effect or our treatment. So to look at that here, if we were to just look at education on wage, we would see that there's a pretty strong positive relationship. But if we were to look at the predicted values of education, which is the more refined approach, it's our alternative pathway to properly measure education on wages by accounting for omitted variable bias. We can see that it's still a positive relationship, but it's not as strong, and that's because we lose some of this relationship power by accounting for the omitted variable. Okay, hopefully that makes sense. It's just a matter of refining that. This is our way of refining the measurements that we could get. Now, I mentioned earlier there's a test we can run in order to see if our instrumental variable is correlated enough with our policy variable. So if we want to test the relationship of our instrumental variable and our policy variable, which needs to be a strong relationship, we can run the first stage. So once again, instrumental variable as our independent variable, we'll just include ability because it was a control, so we include the control. And then education, which we include here as our outcome variable. We run this model and we check the F statistic. The rule is that the F statistic has to be at least 10 or the instrumental variable would be considered a weak instrument. So a general rule is F statistic has to be at least 10 or your instrumental variable is not going to be good enough. And we can see here that it's far greater than 10. So we have a good instrumental variable. And that ties back to the three criteria that you need for an instrumental variable. You can always reference that at the earlier part of the lecture as well. Now, if our relationship between our instrumental variable and our policy variable is weak, it's going to do a pretty bad job in approximating the effect of the policy outcome. And that defeats the whole purpose. So that leaves bias in our estimate. So sorry, class, I accidentally stopped recording and I had to restart. So when I merge these videos together, if there's a little gap or a pause, I apologize. All right, so getting back to it here. So again, instrumental variable has to have a strong relationship with our policy variable, or else it's going to do a poor job in helping us get a proper estimate of our effect. And need to have strong evidence that the instrumental variable does a good job in approximating the policy variable, and that's the F test. So just remember that. Okay. And as we talked about before, so because the instrumental variable is going to have a strong relationship with the policy variable, as a byproduct, that means that our instrumental variable is also going to be correlated with the outcome, which we can see here shortly. But we need to make sure that it's only through the, visually we can see this again, that it's only through the policy variable is our instrumental variable correlated with our outcome. So let's look at this visually. We have father's education on hourly wage. So we have our outcome variable and we have our instrumental variable. We see a uh, positive relationship, but it's important to be able to argue that the correlation only exists through. So once again, we want our instrumental variable to affect our outcome variable only by pressing on our treatment variable. We don't want there to be an alternative direct relationship The bottom line is we don't want a direct relationship between instrumental variable and outcome, or else it's not going to be a good instrumental variable. So think about it as z pushes on x1 in order to modify y. So like we've discussed in this example, we're arguing that a father's education increases hourly wage only if it makes an individual stay longer in school. So father's education influences education for their children, and then that influences their children's wages. Now this direct relationship, or sorry, the absence of a direct relationship between instrumental variable and outcome variable, that's going to also be argued through theory and some studies. So you're going to have to be able to really state your case. So moving on, this is just going to be the correlations for all of our variables here. You all should be familiar with this visually. So we can see if we look at each of the relationships, let me zoom out so we can see it all at the same time. We have wages, education, ability, our omitted variable, experience, that's going to be our control, and father's education. So outcome variable here, education is our policy variable or treatment variable. Ability is our omitted variable, which we cannot measure. This is, if we could measure it, this is what we had. This would be the perfect world, but we really can't measure it. Experience is our control, father's education, instrumental variable. We can see that the relationship between experience and father's education, it's not significant. The relationship between ability and father's education is not significant. However, the relationship between education and father's education is significant, which that's the treatment variable. So it has to be an instrumental variable to be effective, has to be strongly related to our treatment variable. And once again, father's education and wages, our outcome variable, is also related. However, it's only through education, like we've discussed. So now, bottom line here, instrumental variables can be they're required essentially very important to in order to gather the most accurate, efficient, and unbiased results. But they can be challenging. So you got to be creative in how you come across this. Utilize a theoretical framework developed from previous studies, and then make sure that you're assessing the correlation between your model variables. And there's a good package called Core Plot, which is really helpful for doing that. So now, if we were to look at another study, we'll look at this one here, and you can access the data as always too if you wanted to run through this yourself. Working with 3,010 observations, and we're going to be looking at the same thing. So it's just the actual data. So we have our annual wages, education. This one's not father's education that we're going to be working with as an instrumental variable. It's going to be proximity to college, so living close to college, listed as a dummy variable. And then we have some other controls: living in a metropolitan area, years of experience, black, and living in the South. Okay. Okay, so the question we were looking for is the impact of education on wages once again. The thing that's changing is our instrumental variable is now going to be proximity to college. And there's arguments to support why that's going to be effective, but remember your instrumental variable has to satisfy three things. It has to first satisfy the correlation or the relationship between your policy variable and your instrumental variable, so they have to be related. So in here, they say individuals who live close to a four-year college have just easier access to education at lower costs. They don't have to worry about commuting, the time spent commuting, nor extra accommodations to be closer. So they have greater incentives to pursue it. So again, they're arguing this relationship as well, or this rationale. But again, it has to be related. Instrumental variable and the policy variable must be related. The second requirement is it cannot be correlated with the omitted variable. And the rationale here is individual ability does not depend on proximity to college. You can live far away from a college and still be highly capable and very high ability. And the last requirement is it is correlated with the dependent variable, but only through the policy variable. The explanation here being living close to a college has no effect on your income unless you decide to pursue further education because you live closer to a college. So there's an example of everything we've been talking about in play. We have our first stage model. Our treatment variable becomes our outcome variable. Our instrumental variable becomes our treatment variable, and we make sure to include all of our controls. Once we run that model, we take our fitted values, x1 hat, which again is fitted. So in this case, it would be fitted at the fitted function, and then we would include whatever our object is we save our model to. And then we run our overall question. Wage is the original outcome variable we're looking for. Education is replaced with our x1 hat, and then we include our control variables. So let's look at some of the data, some summary statistics. For those of you not exposed yet to regex, you'll notice here that in order to um, isolate education. This data set has variables like father's education, mother's education. So in order to make sure you just get education, this is regex. It's a way to work with strings. So all it's saying is that it has to start and end in this way. So it has to contain education only. It has to start there and end there. So it has to start with an E, followed by a D, U, C, and there with the C. So that's something called regex. It's really helpful for working with strings. If you have not been exposed to it, it's not necessary at all for what we're working with here. Okay, so let's go ahead and plot these. So we can see the distribution here of our dependent variable wages, and we can see the distribution of our education, our policy variable. And then we can also see a breakdown of the number of people who live near a four-year college and those who don't. 0 representing do not live near a four-year college, and then 1 representing those that do. As mentioned before, we want to make sure we're testing our instrumental variable using a F statistic. So when you run your first model, you want to make sure that your F statistic is more than 10. And we can see here in our instance using the first stage F statistic of 448, so we know it's more than 10. So we know that our instrumental variable is reasonable there. So we have our models here. So education, that was our treatment variable, our overarching treatment variable, but we include that here in the first stage as an outcome variable. Then we include our instrumental variable as the treatment variable for the first stage, and then include your controls. As mentioned once again, use the fitted function on the object you save your model to. You can attach that to whatever you want, but ultimately it's going to be the x hat or the x1 hat because that's the coefficient we're looking at. And then for your second stage, you're going to be taking your original, your overarching outcome variable you're looking at, and then you're going to be including your fitted predicted values as your treatment variable for stage 2. And then we run these. And this is an interesting situation where instead of our model not including, pardon me, scratch everything I just said. I was getting this mixed up with a naive model, so forgive me. We have our first stage, and then we have our second stage. So our, based on our predicted values, our best refined estimate of education on wages is this value here. And once again, I don't recall the exact circumstances or how this translates. I don't recall that context. We can go back and look, but that's not necessary for this lecture. Okay, so that's how we do our instrumental variables. Fairly straightforward. You're just going to go through part 1, part 2. Let me dive over to the PowerPoint section. And pardon me, before I move on, okay, and sorry, I had to pause for a moment coming back to it. So again, here's the IV-reg function. Show you an example of how that works. So we have our simple model here, which is what we've been working with, just the lm function. If you want to do the IV-reg function, basically what it does is it allows you to do both stages in one. So you can see here, you go ahead and list the original function. So we have our wages, our starting outcome variable we want to measure, education, our treatment, then our controls. You're going to include the bar here, though. This is what's going to allow you to separate this first and second stage. So we initially put in our second stage, technically, but the first stage here, you put in the bar and you're able to drop some minus education. So we take away the treatment variable for which we would use in our original model. And instead we add in our near college, our near C4. That's going to be our first stage component. And then put in your data. And this will allow you to populate everything at once. One thing I didn't go over with you guys though is how to more clearly interpret um, the coefficients. So, and it actually doesn't go over it in the lecture, but there's a concept called local average treatment effect. Basically, what that's referring to is um, when we do use an instrumental variable, it changes how we interpret our coefficients. So, I guess let me try and do it this way. Bear with me here. So if we're using in this example, we use the instrumental variable near for your college, which again, that's a dummy variable, labeled 1 if you're near a four-year college and 0 if they weren't. Going back to that example where we're looking at the covariance, because we have here in this example, we have our instrumental variable, which is near C4, and then we have our X1, and that is our education. So again, education is our treatment variable that we want to know how it affects income, but our instrumental variable we use that to try and compensate for the omitted variable bias. So we want to look at this overlap. So this is why I want to bring it up because we're using uh, our shared variance here, our covariance between education and the near C4 variable. This combination or using an instrumental variable changes how we then interpret our coefficients because we're using the shared variance in order in our final model. Our final model, let me just tell you. So our first outcome, if we do the first stage where we have education as our outcome variable and near C4, near a four-year college as our treatment variable, our coefficient here is going to be straightforward. We know that for every, or sorry, for being near a four-year college, you're going to get the average would be an increase of education. You'd have an extra 0.33 years of education. However, when we then take the predicted values from this first stage and apply it to our second stage model, this interpretation now becomes a little bit more narrow. So instead of this being, and it has to do something with something called compliers. In our case, compliers is going to be representative of those whose decision to attend college was affected by their proximity to college. Okay, so keep that in mind. So we're essentially we're narrowing down um, our population that we can extract this or apply this to be the population that is those whose decisions were affected, the decision to go to college, excuse me, was affected by how close they were to a college. So now our result here is not representative of the entire population. So this would then be representative of those whose decisions to attend college was affected by their proximity to a college. And we would now interpret this as the same as we normally would, which remember wages is in log form. And when we look at logs, we'll go over this later. But generally speaking, if you're working in log form, your coefficient, you'd interpret that as a percentage. So this is saying for every additional year of college, um, a increase of wages of approximately 16% would be expected. You just put that in a percentage form, and that's kind of the quick reference. If it's a small number, it just approximates it. It's not exactly that, but we'll cross that bridge when we get to that module. But the biggest thing I want to harp on here is this is not representative of the total public. Instead, it's representative of those whose decision to attend college was informed by their proximity to college. So I just want to point that out. It doesn't share that in the lecture. Pardon me, it doesn't clarify that, but I just wanted to pinpoint that because our interpretation does change a little bit, where this case is not representative of everybody necessarily anymore. It is representative of those um, whose decision to pursue higher education was affected by their proximity to a college. So our translation of that coefficient changes just a little bit. So keep that in mind. Depending on your instrumental variable, you want to think about how that would then affect your coefficient. So let's say hypothetically we have, I'll write it out here. Let's say we are working with, we want to know the outcome of tobacco use on heart disease. We'll say that. So our heart disease is our final outcome variable. Still can't, I don't know why I can't do the squiggly line. Sorry. Uh, Heart disease is our outcome variable, and tobacco use is our treatment variable. In order to account for emitted variable bias, which could be a number of things, could be just predisposition to risk. It could be a number of things. So either way, let's say that we want to use a instrumental variable of tobacco tax, and let's say that it satisfies all of our requirements. And I'll just tell you the reason I'm using this example is I believe it is. So it's actually another example that's listed here. So tobacco tax, our instrumental variable, emitted variable, other negative health behaviors, and then policy variable, tobacco use or smoking cigarettes, outcome variable, health. So we're just narrowing that just a hair. Um, so we use an instrumental variable for tobacco tax. That being said, our stage one, okay, why is my lettering not showing? Stage one is going to look like our treatment variable becomes our outcome variable. So that's going to be, I'm going to call it TC for tobacco use. And our instrumental variable becomes our treatment variable. So that's our stage one. And then our stage two then would be our outcome variable, which was heart disease. I'm going to call it HD. And the fitted values or predicted values from our stage one. If we were to look at this example, when we interpret our coefficient is because of the steps we're going through in the use of a tobacco tax. Our interpretation of the coefficient for the x1 hat, it's still going to be the same value. However, the applicability is that now going to be refined, where our interpretation is going to be sort of subsetting the population to where it's only going to be representative of those smokers, the tobacco users, that were affected by the tax. So if their decision to use tobacco was affected by the tax, our coefficient for this would be representative of that population, not the population as a whole. So a small detail, but keep that in mind. If you need additional clarification on it, let me know. I wanted to point that out because if we were to run a naive model for the same education example, and then compare that to our second stage instrumental variable coefficients, our impact of education on wages is less than what it would be with our instrumental variable, which is different than what we had looked at previously, where when we were explaining it, it actually should have reduced our impact. Forgive me, I'm scrolling all the way back here. I probably overshot it. Give me one second. I'm going to pause. Oh, here, I'll just use this. No, give me one second. I'm going to pause. I'll be right back. Okay, I was just a moment away from it. So I was trying to find this table. So looking at the example where we used, shoot, what was it? Father's father's education as our instrumental variable. We use the prediction from that. Uh, so we would expect from the naive model, which again absorbs or it assumes, I should maybe say, some of the predictive power from the omitted variable. So it over exaggerates the effect. So when we include the instrumental variable, it actually decreases that effect. So that's what you might expect, but I wanted to point this out because in this final example, we get a reverse where we find that when we run a uh, naive model, our education effect is actually less than what we find in our predicted or instrumental variable stage two model. And I just want to point that out because the reason the education is lower here is this is now taking into consideration the entire public and it contains the bias, but it's going in a different direction because it's taking a look at the entire population. So it's weighted downward. Um, and that's why we have a higher value here for our uh, second stage instrumental variable model. I hope that makes sense. If you have questions about it or anything, let me know. But the biggest thing to keep in mind is that by using the instrumental variables, we do lose a little bit of generalizability because we're sort of subsetting our population based on our instrumental variable. I don't think any of this matters for our lab, but it is something important to know about interpreting coefficients. So keep that in mind. And then again, if you want to play around with IVReg, you're more than welcome to use it in the lab. You don't have to, but it can streamline and it takes away some of the steps from um, pardon me, from doing the two stages separately. Okay, now I wanted to come over here and finish up just on this slideshow. We've pretty much covered everything you need to know. This is going to be synonymous once again with what we learned in lecture, just more visual representations of it. Me, everybody, my headphones died. I had to pause the video. Wanted to come back to the slides, so you can go through the rest of this on your own. And again, just visually covers what we had already gone over in the lecture. Just slightly different visualizations. So I just wanted to recap this. When we use the instrumental variables, or sorry, we use them when, one, we know that we have an omitted variable problem, that when we know we have an omitted variable that will cause bias. We don't have a way to include it, such as like the ability, that we don't have a way to measure that. Or there's other examples earlier in here where number of criminals was an example. We don't have a way to measure the number of criminals, so we find an instrumental variable that helps us to get there. And then we have an exogenous variable, which to recap, exogenous is just another way to describe. Let me show it to you visually here. So it's taking longer than I thought. There we go. So exogenous. This is the way. This is the word to describe one of the requirements of our instrumental variables. It is the idea that it is unrelated to our omitted variable. So exogenous, it's correlated with the policy variable here, but not with the omitted variable. Okay. So when we hear exogenous, just think of number three, the uh, criteria that we go over in the lab. Okay. So coming back down. So exogenous. And then to recap again, a lot of the to do with the instrumental variables are justifying through logic and theory. Like we saw, there are some tests you can use, like the F statistic test, uh, some of the correlations, but it's a lot to do with a good story and having a good rationale or justification for it. And then again, recapping first stage, we already went over that. We predict the treatment variable using the instrumental variable, and then we use the predicted values in order to determine our for our second stage, excuse me, use the predicted variables to determine our original outcome variable. Okay, so that's the gist of it, everybody. Reach out if you have any questions. Good luck on this week's lab. Thank you for your time. We'll talk soon.